We've reached an important milestone in the course. In the previous set of lectures, we have derived the governing equations and the jump conditions at an interface. In particular, we saw that if you have surface tension and curvature at an interface, the normal stress balance tells us that there could be a pressure discontinuity across the interface. And similarly, in the case of tangential stress balance, we saw that if you have gradients in surface tension, then we will have an additional tangential stress at the interface, which will lead to a flow. The governing equations and the boundary conditions are now sufficient to tackle various interesting problems in interfacial flows. We will begin by looking at problems in capillary statics. And as the name suggests, these are problems in fluid statics, that is, problems where there is no motion of the fluid at all, but with capillarity as an important contributor. Now, I'm showing you three images. Now, in the first case, I'm showing you a pendant drop. This is a drop that is hanging from a tiny needle. This is the kind of drop that would form basically when you partially open the tap and close it. Then you have a little bit of water that is suspended from the mouth of the tap. And then the second image is a meniscus. This is basically the deformation of the fluid when it basically meets a solid. So if you dip a straw into a glass of water, you will see that right around the straw, drinking straw, you'll see that the meniscus interface bends. And in the third image, I'm showing you sessile droplets. These are droplets sitting on a solid plate, but with different volumes. Now, what is common in all these three problems? A, all of them are static problems. And two, these problems are governed by two things that are common is all of them are different shapes. But there are some common forces that are at work. For example, gravity is important in all these three problems, and so is surface tension. And notice that these problems also have curvature. Therefore, we will be using the problems from hydrostatics, which is how the pressure varies across a fluid when there is gravity. And at the interface, there is a discontinuity in the pressure, which relates the pressure jump across the interface to surface tension and curvature at the interface. Now, in problems in capillary statics, we'll be looking at a variety of interesting problems. We'll begin by looking at the shape of a meniscus, and then I'll show you two different ways of arriving at the same conclusion. For example, we could use a force balance approach, that is, we'll use the jump conditions at an interface and obtain the shape of a meniscus. But we'll also look at another interesting approach, which is minimizing the energy, the total energy of the system. So we will look at problems in energy minimization, and we will have to look at the problems in calculus of variations, and I'll be deriving the classical, very important Euler-Lagrange equation. And then we will be looking at how the Euler-Lagrange equations can be used to obtain the shape of a meniscus. And then we'll be looking at problems in wetting. You already see one example of a wetting, which is a sessile drop sitting on a plate. Now we want to determine a simple question in this problem could be, what is the shape of the droplet? What is the shape of the droplet which is subjected to gravity and surface tension? Now clearly you should, you can clearly see that the shape basically differs in all these in the various drops that are shown, not just because they've become the droplets have become bigger and bigger, and therefore the volumes have changed, also because the relative balance of surface tension and gravity has also changed. We will, after looking at the problems in wetting, where we'll be looking at the so-called Young's law, we'll be looking at more complex problems in wetting, especially wetting on surfaces which are not perfectly smooth. So we'll begin the discussion by looking at the shape of a meniscus. And what I will first do is to obtain the shape of a meniscus using the force balance approach that we've already obtained. That is the normal stress balance that we have obtained. Now, let me first draw the problem that is of interest. So this is a static meniscus. Now, the problem setup can be thought of this way. So I have, this could be the vertical plate, and along the plate I've taken a coordinate system Z, and I have a liquid so this is the original we have a flat liquid, and the moment I dip a plate into it, then let us assume that the interface basically deforms. Now there is a certain angle that the interface makes. We'll call this as theta E or theta Y. Well, let's call it theta E. And this bending that you see here, this is my meniscus. Further, we have gravitational force. So we have a gravity that's acting. This is a vector. So this is minus G times Ez, where Ez is the unit vector in the vertical direction. We also have an atmosphere at a constant pressure. This is atmospheric pressure. We could consider it could just be air, and here we have a liquid. Right? So let's define the normal vector at any point to be n hat. This is going from liquid to the gas above, and we will also define the position of the interface. The position of the interface is given by Z is equal to h of x. So we'll consider a two-dimensional problem. So my x is in the horizontal direction as Z is in the vertical direction, and I've chosen my coordinate system in such a way that the origin is where the flat interface from the far field meets the plate. Okay. So let's start with writing down the momentum equation. Now the momentum equation, the continuity and momentum equation would be as follows. We have del dot u is 0, rho naught du bar by dt is equal to rho naught times g minus grad p plus mu del square u. This is my Navier-Stokes equations. Now clearly this term is identically 0 because we have no velocity, and again we have no velocity, so these terms are identically 0, right? And therefore what we end up having is rho naught times g bar is nothing but grad p, and this reduces to two equations in two dimensions. Del p by del x will be 0, and del p by del y will just be minus rho times g, because remember my gravity vector g bar is minus g times Ez, because my z is pointing upwards and gravity vector is pointing downwards, and therefore I can just simply have pressure. So this should be z, pressure at any point here would be any z point would be p naught minus rho naught g z. Just correct this should be rho naught. Okay, so we have basically got the pressure at anywhere in the fluid. Let's call this equation 1. So this tells us that if I am at some arbitrary location Z from the bottom, then the pressure at that point P will be P naught minus rho gz. And what is P naught? P naught is the pressure at Z is equal to 0. Okay. Now notice that if I take a flat interface, then if I take a meniscus far away from the plate, that is when X becomes very large, the interface becomes flat, and when the interface becomes flat, there is no curvature, and the pressure across the pressure is continuous across the interface. Now we will also, the density is also constant that we are going to assume. Now the pressure jump across the interface, if you have curvature, then the pressure jump is given by the Young-Laplace equation. So normal stress balance essentially says that the pressure, so it is not the Young-Laplace equation, the Laplace pressure jump is just minus gamma times del dot n. Now what is minus and plus? So if I take a part of the interface, any part of the interface, a little above and below, the minus would be below and plus is above this meniscus. So therefore I can now relate what's the pressure across the interface at any given location in terms of the local curvature and the value of surface tension. Okay. Now gamma is surface tension. It is constant for us. Okay. And we also know that pressure above is nothing but P naught, and the pressure below at any location is will just be P naught minus rho gz at as Z approaches the interface from below. So we can say it is H minus. So this is nothing but P naught minus rho naught g H of x. So we can now substitute this into the pressure discontinuity that we have here. P plus would be P naught and P minus would be P naught minus rho naught g H of x. This will be minus gamma times del dot n. The P naught cancels out on both sides, meaning the pressure above does not matter, and this simply becomes rho naught g H of x becomes minus gamma times del dot n. Now what is del dot n? For example, if I take let me make a simple sketch of this meniscus again. If I take a meniscus which is like this, and if the height anywhere is Z is equal to H of x, where this is Z and this is x, then I can calculate the normal at any point here. The normal vector can be obtained by simply getting the defined by taking the gradient of a function f divided by the magnitude of the gradient. And what is this function f? This function f is defined in such a way that f is equal to 0 is the interface, and you are above the interface, f is greater than 0, and if you're below the interface, f is less than 0. Therefore, what we now have is we now have f of x comma z is nothing but z minus h of x is 0, and therefore n hat, which is gradient of f, by magnitude of gradient. This simply becomes, this is the normal vector where gradient of f is given by del f by del x ex plus del f by del z ez, where ex and ez are the unit vectors in the x and z directions, and this quantity essentially becomes minus dh by dx ex plus ez, and therefore I have magnitude of this gradient simply becomes 1 plus dh by dx whole square. Okay, so we will use a slightly shorthand notation to write this. Instead of writing it as dh by dx, we'll just simply write it as h subscript x ex plus ez, and therefore this becomes 1 plus hx square. The subscript x denotes that we are taking a derivative of x with respect to x. So the normal vector now essentially becomes minus hx ex plus ez divided by 1 plus hx square, right? And this is two parts here, minus hx by 1 plus hx square ex plus 1 by 1 plus hx square ez. So we can think of this as the x component of the normal vector and the z component of the normal vector. Therefore, curvature del dot n will be del by del x of nx plus del by del y del by del z of nz. We will be doing these calculations a few more times in the course. Here we are doing it for a static meniscus. We may repeat this calculation for the curvature of an interface even when it's not a steady problem or a static problem. But it's worth going through this exercise a few more times so that all of you get some practice for doing this. And if we do this calculation, then I will skip the detailed algebra here. We have to take the x derivative of nx and we have to take the z derivative of nz. Clearly, the second term is identically 0 because nz is not a function of z. And if we just do this calculation, we have hxx divided by 1 plus hx square whole power 3 by 2. This is del dot n, right? So we've got a few important results here. Equation 1 tells us the relationship between the pressure at any point because of gravity, variation of pressure in the meniscus because of gravity. And equation 2 that I'm just marking now, this tells me the relationship between the potential energy rho g hx and capillarity or surface energy minus gamma times del dot n. And finally, we've got an expression for curvature, that is equation 3. Now we can simply substitute this 3 into, if we substitute, we simply get rho naught g h of x will be minus gamma times del dot n, and del dot n is nothing but minus hxx by 1 plus hx square whole power 3 by 2. This is nothing but gamma hxx by 1 plus hx square whole power 3 by 2, right? So we can also rewrite this as hxx by 1 plus hx square whole power 3 by 2 is nothing but rho naught g by gamma times h of x, right? Now, I had basically made one important simplification. Now the pressure above I said is a constant atmospheric pressure. I did not take the density of the fluid above into account. Strictly speaking, maybe I should make a note here. So strictly speaking, the pressure at any point in the meniscus should actually be P0 minus rho of the fluid rho minus the rho above, let's call it a rho gas, times Gz. This is the correct expression that we have, but we can basically absorb this rho G into the this rho G term does not matter, because without any loss of generality I can ignore it. So because the density of the gas is so much smaller than the density of the liquid in most cases. For example, in the air water, the density of the air is 1,000 times smaller than the density of water. So we have basically assumed it to be negligibly small. Otherwise, we would actually get a density difference. Okay. So recall that we have already derived the capillary length. The capillary length would be gamma by delta rho to G, and this reduces to gamma times rho naught into G, because the atmosphere above density is neglected, and therefore this simply becomes 1 by LC square h of x. So we've got an important relationship between the curvature term and the capillary length. We'll call this equation number 4. This equation is a non-linear ordinary differential equation. It's a non-linear second order ordinary differential equation for h of x. Okay, so we would need two boundary conditions at two different locations. So the first boundary condition could be I could say at x equal to 0. Recall what is x equal to 0. X is basically varying in the horizontal, so x equal to 0 is really the vertical wall. And note that when x equal to 0, the meniscus is meeting the plate. So my plate is, this is my plate here. The meniscus is meeting the plate with an angle of theta e. The meniscus is meeting the plate with an angle of theta e. So if we write down the boundary condition, if we simply have tan of theta e will be minus dx by dh, or I simply have dh by dx at x equal to 0 will be minus cot of theta e. So we can basically, the idea is the following: we have a small triangle here. So this height is minus delta x h, and the horizontal is plus delta x, and the angle is theta e, and therefore tan of theta e would be delta x by minus delta h, and that's how we got this result. So that's the first boundary condition that we have got, and the second boundary condition essentially becomes, as x goes to infinity, meaning in the far field, interface becomes flat, and this essentially means that the height of the meniscus goes to 0 as x goes to infinity. So now we have two boundary conditions. Let's summarize the main equations. The summary is as follows. We have d square h by dx square is equal to 1 by lc square into 1 plus dh by dx whole square whole power 3 by 2 times h of x. This is a nonlinear ODE with dh by dx is equal to minus cot theta e at x equal to 0, and h of x goes to 0 as x goes to infinity, right? So this is basically my full equations. We can also eliminate the capillary length from this analysis by redefining the meniscus. So for example, one way to do this is you can define non-dimensional version of the same equations. What would be the non-dimensional version? We say let capital X be x by LC and capital H be h by LC. Then I would like all of you to try and do this on your own, but if we systematically do this correctly, then we get d square capital H by d capital X square will simply be 1 plus d capital H by d capital X whole square power 3 by 2 times h as a function of x, with the first boundary condition anyway is non-dimensional, minus cot theta e as capital X at capital X is 0 and h of x goes to 0 as capital X goes to infinity. Now why would we want to do this? This essentially says that meniscus shape can be obtained in a universal fashion without knowing the value of capillary length. So even if I don't know the value of the capillary length, I can still determine the shape of the meniscus. The only thing I need is the angle, and then for different fluids we can rescale the shape of the meniscus to get the exact shape if I can solve these equations. So there is some universal aspect about these equations because I can absorb the capillary length. Okay, now how do we solve this? Well, there's no simple way to do this because there is an exact solution available, but the exact solution is too tedious, and it also clouds the essential physics in the problem. So what we will do is to try and get an approximate solution of this equation. Now the idea of getting an approximate solution is to assume that you see that here in the curvature term we have a nonlinearity. This term in the square brackets, which is 1 plus dh by dx whole square whole power 3 by 2, that term is the culprit. It's nonlinear, and therefore getting a simple solution of this equation is not so straightforward. What we'll be doing in the next lecture is to come up with an approximate solution for this equation with the assumption that the slope is small, and then we will obtain the shape of the meniscus in that approximation. This will allow us to compare the solution that we've got with the energy approach that I'm going to do next. So see you in the next lecture.